At the turn of the 21st century, ultra-fast physics was undergoing a revolution. The driving force was lasers. As researchers honed their skills, a universal tape measure began to emerge, a tool to count the ripples of a light wave.
This tool is known as a frequency comb, but how did a comb allow us to measure to such unprecedented levels of precision?
In 2005, John Hall and Theodore Hansch were awarded half a Physics Nobel Prize for their work on laser-based spectroscopy, and specifically for their contribution to the laser frequency comb. After the inception of the laser in the 60s, there were two competing factions, those who liked great power and those who liked calm stability. Theodore Hansch was one of the pioneers to attempt to unite the disparate fields and create high-repetition laser pulses. His team's development of the mode-locked femtosecond dye laser opened up the field of spectroscopy and allowed investigations into the spectral lines of hydrogen. Here, they measured the Lamb shift of the alpha-Balmer line. The Lamb shift was not predicted by the Dirac equation, and so began the field of the relativistic study of light-matter interaction, quantum electrodynamics. In 1978, Eckstein, Ferguson and Hansch measured the fine splitting in sodium spectral lines and demonstrated the true precision in their mode-locked continuous wave lasers. At the same time, developments in gain media, away from the delicate and carcinogenic dye lasers, were being conceived. A pivotal moment was in 1982 at MIT. The titanium-doped sapphire laser was born. And 7 years later, at St. Andrews, Kerr lens mode locking led to stable pulse trains. When a laser pulse is intense enough, focusing it on a transparent material will spontaneously generate white light. White light generation was demonstrated in optical fibers that incorporated air holes. These air holes allowed the refractive index to be drastically varying radially. Numerous other optical fibers were made, like tapered fibers. They were dubbed magic rainbow fibers. In Boulder, Colorado, John Hall's team monopolized on these magic fibers and controlled the tricky carrier envelope offset frequency. In Garching, Germany, Theodore Hansch also managed to synthesize octave-spanning combs, and together by 2004, their combs had reached stunning precision and were set to create standards for the meter, the second, and the fine structure constant.
A frequency comb may be generated in many different ways, most commonly using a mode-locked laser. Other methods include using four-wave mixing, electro-optical modulation of a continuous wave laser, and even using electronics. I'm going to focus on the mode locking laser technique. So to start off, I'm going to show you a basic laser diagram, which consists of two mirrors, one which is completely reflective, and another which is partially reflective to allow the outcoupling of laser light. These both contain a gain medium in this optical cavity, which contains laser active ions that can be excited by a light source. So the reason we want to excite these laser active ions is so we can achieve a population inversion, and then from that we get stimulated emission of light. And this light resonates in the laser cavity between the two mirrors until it reaches a threshold gain. And as we pass this gain, the laser light is outcoupled from the mirror as coherent laser light. So I've talked about the multiple cavity modes that resonate in the laser cavity, And in a mode-locked laser, we want to achieve a fixed phase relationship, which is best displayed by showing their electric field as a function of time. So I'm going to show a single mode and its neighbouring modes and how the phase relationship looks. So the neighbouring mode is going to be closely spaced to this mode that I've drawn here, which gives the best results in the mode-locked laser. There are going to be millions or even billions of these modes with the peaks aligned in the same position here. And the superposition of these modes result in a Gaussian envelope modulated sine wave, which is shown as in the graph like this. So here we have our Gaussian envelope with our sine modulated wave in here. Back to our basic laser cavity diagram, we can show that the Gaussian pulse will oscillate between the two mirrors. And after each resonator round trip, the pulse is outcoupled from this partially reflected mirror. And this will generate a train of pulses, and the repetition rate will be dependent on the cavity characteristics. And this can include things such as the length or optical properties inside the cavity. The superposition of these standing wave modes may be more clearly visualized in MATLAB, where we can walk through the Fourier transform of the series of these pulses of the frequency cone, which essentially acts as an optical ruler, and is analogous to the tape measure, but instead intervals of length are replaced with frequencies. So if we now move over to look at these modes in MATLAB and progressively add more of them, the Gaussian envelope becomes narrower and results in ultra-short pulses. A series of these Gaussian pulses form an optical pulse train, where millions of different colours are included in a train of very brief, closely spaced pulses of light. Many modes are required in frequency combs, so we can generate extremely narrow pulses in the time domain, which corresponds to a broad spectrum of frequencies in the frequency domain. With a greater set of frequencies, we are able to reference incident light to a wider range of frequencies on this optical ruler. As we observe the time evolution of the pulse, the peak of the oscillation, the sine wave, drifts from the peak of the Gaussian envelope. This is known as the carrier envelope offset, arising due to differences in group and phase velocities from chromatic dispersion of pulse circulation in the laser cavity. This is linked to the phase shift, denoted by delta phi in the diagram on the screen. After each pulse resonator round trip, the offset difference is quantified by this phase shift. The offset is negligible in many cycle pulses, however, the effect is much greater when very few oscillations are modulated under the Gaussian envelope, as the phase shift becomes a significant proportion of the pulse duration. The pulse repetition rate is easily measured with a fast photodiode. However, it is more difficult to measure the carrier envelope offset. F to 2F interferometry measurement is required. This is a method that allows determining absolute optical frequencies with octave spanning spectra, which is a spectrum that spans from a set frequency through to twice of that value. So here we have an octave spanning spectra of our frequency cone, and we want to find the carrier envelope offset frequency, denoted by F0. We first pick the mode Vn and double it, giving double the frequency, and deduct the frequency located at the other end of this octave, V2n. This gives us the offset frequency that we are looking for.
Okay, let's look at a graphical representation of how we determine an unknown frequency using our frequency cone. So let's define an axis in frequency space. Here's omega, and naturally our frequency cone is evenly spread out along frequency space. So we have our almost infinitely sharp peaks Their intensities don't matter, but we usually follow a Gaussian profile. Next, we mix in an unknown frequency that we want to determine. Here. Now, these teeth, we really accurately know what frequency they are. So we'll call that omega naught, omega 1, omega 2, etc. And then this difference here between our unknown frequency and that tooth, say, we'll call delta omega. What happens after mixing is this signal is modulated into a beat note, which gives us information about delta omega, and then we just add that on to omega naught, and there we go. We found our frequency.
Astronomers also use frequency combs, utilizing their ability to redefine frequencies for exoplanet searches. The most prevalent method is by using spectrographs, and one of the most well-known spectrographs is found in the La Silla Observatory in Chile. Exoplanets are planets beyond our own solar system, and in the never-ending quest to find out if there is life out there beyond Earth, astronomers, astrophysicists, and other researchers use this equipment to scan the sky looking for potential planets. The spectrograph is designed to look at wobbles that a planet induces in a star's rotation. The High Accuracy Radial Velocity Planet Searcher, abbreviated to HARPS, has found well over 100 exoplanets itself, and is regularly used to confirm observations from the Kepler telescope and other observatories. These are instruments that separate waves of information into their array of different frequencies. Using spectrographs, researchers are able to detect the very subtle movement of a star when a planet approaches or departs. The result, described as a wobble, not only alerts researchers to the presence of a planet, but gives up clues regarding its size, density, and other properties. Until now, however, even the best spectrographs could only offer information about large Jupiter-sized planets that venture very near their star, causing a wobble strong enough to detect here on Earth. Implementation of frequency combs allows detection of more rocky, smaller, and distant exoplanets by calibrating the spectrograph and converting the optical frequencies into a lower frequency range, described as the frequency comb acting as the gears of a clock. But what does this achieve? By transposing the optical frequencies down, we are able to access a much finer resolution of frequency to a smaller uncertainty and a greater precision as a result. The end result of implementing this new technique should be the discovery in coming years of more and more exoplanets that are smaller, cooler, and farther from their star, much more like our own, perhaps one day leading to the discovery of one that looks like ours and has the ability to hold life.
The story goes that Galileo was in a church when he noticed a chandelier sway back and forth. He measured the period of oscillation with his pulse, and he realized that the height of its swing didn't affect its motion, and so was the basis of pendulum clocks. Every clock needs a pendulum. This grandfather clock oscillates at once a second, and the quartz resonator in your watch at about 30 kilohertz. But to find true precision, they needed to find a pendulum that was a lot faster, and therefore we developed atomic clocks. By 1990, work on atomic clocks was well underway. These clocks were to take their penduli to be the electronic transitions in a molecule, atom, or ion. One such clock that has become the ubiquitous time standard is the Caesium fountain clock. In Caesium, the valence 6s electron is split between two hyperfine energy levels, and we can use a microwave resonator to probe that transition. By using a different atom, like aluminium, strontium, or ytterbium, we go away from a microwave transition and into an optical transition, once thought to be too fast to measure, but by 2013, by implementing optical frequency combs, these optical atomic clocks have become an order of magnitude more precise than the Caesium fountain clock. There is now an international system of synchronized clocks. The only problem is that time isn't constant across the world and depends on your local gravity. So wouldn't it be nice to have a clock in space? Menlo's Systems have recently sent double-combed optical clocks into space based on rubidium atoms. Their aim is to test Einstein's theory of general relativity to see how gravity affects time. NASA are developing deep space atomic clocks so their missions will have their own navigational clocks on board instead of referencing all the way back to Earth. That concludes our presentation on frequency combs. If you enjoyed it or just enjoyed chemistry and physics, then be sure to check out ChemPhys at Uni of Edinburgh or at other institutions across the world.